as we're graphing, we're going to start with the sine graph, and we're going to be doing these on our calculator. But when I taught you radians, one of the things that I taught you was that a radian's biggest difference in its basic measurement tool is that an angle measured in degrees is just a count of how much of a rotation you've made. An angle measured in radians is counting not just rotation, but also the size of the radius. That's why it's called radians, because there's a very strong correlation there. So when we're doing graphing, the most common thing to graph is a comparison of distances. So for our purposes, we are always going to graph in radians. We can graph in degrees, and it will look very much the same. The difference is largely what it is you're measuring, but we are going to stick to radians. My purpose there is twofold. One, it gets you used to radians, and two, it gets you to learn to count by radians, which is a very important skill when you get to calculus. So we're going to start by practicing our count by radians, and for the first several graphs that you did, I've put the table on there, but it's not quite complete. You'll recall when I taught you radians, I stood like the clock at the front of the room, and I put my left arm out towards the positive x-axis where the 3 o'clock hour would be, and I put my right arm on top of it, and my right arm rotated around in a counterclockwise rotation as I counted. 1 pi over 6, 2 pi over 6, 3 pi over 6, 4, 5, 6 pi over 6, 7, 8, 9 pi over 6, 10, 11, 12 pi over 6. And that's all you need to do to get the table of values in radian mode onto your paper. So I've put the pi over 6's here. You are going to count, there's the 0, I filled it in. 1 pi over 6, 2 pi over 6, 3, 4, 5, 6, 7, 8, need to scroll, 9, 10, 11, and 12 pi over 6. Now on the clock, that's not exactly what I see. Why is that not exactly what I see? Because they're reduced. You're welcome to reduce them, but I don't need you to. You can leave them just the way they are. The second thing that I need you to know is that if we're going to be graphing in radians on our calculator, we need to make sure that our mode is in radians. So would you please get out your handy dandy graphing calculator, hit the mode button, and go down to and hit enter. Okay, so I've gone to my mode, I've put it in radians. Now I'm going to go to my table of values under the stat key. And I want you to hit stat and then enter. This is the first time we will be using lists. Now I know many of you use my calculators, and if you use my school bus yellow calculators, there may be something in your lists. Have I ever showed you lists before? I didn't think so. So we're going to work with lists a lot through the end of the year. They're great for generating tables of values. In order to put stuff in a list, you have to have it empty. So we're going to start by teaching you how to clear a list. There's actually 2 ways, but the easier is this way. I want you to use the up-down arrow key and arrow up until the L2 has a black square over it, or the L1 has a black square over it. Now this is important because I don't want you to get frightened. You need to hit the clear button. Nothing seems to happen when you hit that, but when you hit the down arrow key, it clears it. Now the reason that's important is because it seems like delete would do the same thing, but the delete button will get rid of the whole row, like L2 will be gone. And that could freak you out. It's fixable, but it could scare you, especially if you're in a test. So just remember to use the clear button. I don't want to get rid of the row, I just want to empty it out. Okay? Now I'm going to clear out my other row. I'm going to clear out list 1. And now I have an empty set of tables to fill in. There are 6 lists there. That's usually enough for our purposes. For some of these, we may need 5 of them. I don't think we have any examples that will need 6. But in the first list, we're just going to put those radians. So very literally, we are going to type 0 pi over 6. I hit 0, second caret divide 6. To get that, your calculator will put it in decimal form. 0 of anything is just 0. But when I hit 1 pi over 6, it's going to turn into a decimal. That decimal is the equivalent of 1 times 3.15, get it, divided by 6. That's okay. I want you to finish typing in all the way up to 12 pi over 6, please. Okay, so we've got all those values in our table. Now we're going to come back over here and we're going to talk about essentially what is it that we are doing when we are filling in this table of values. So I've got this table of values. Effectively, I could put in the exact values here, and that'll be fine and dandy. The exact values, say, for instance, for sine of 60 degrees, which is 2 pi over 6, would be rad 3 over 2. So if I wanted to, I could put a rad 3 over 2 here. It would be my y value or my height. The problem becomes, I don't know how to graph that. So when we're graphing the exact values that we've studied, they don't do us jack squat because I can't graph an exact value. To be fair, about as much as I can graph is a tenth with any accuracy. And even that is kind of fudgy sometimes. It depends on how small the graph paper is. So having an exact value when you're graphing is far less important. It's very, very important when you're talking about exact values, but not at all important right now. And that's why we're going to go to the graphing calculator. What I really need are the decimals that would be the equivalent of 0, 1/2, rad 3 over 2, and so on. And the calculator will get those decimals for you uber easy if you arrow to the right and then to the north and then tell the calculator what it is you want. And essentially what it is you'd like to know is the sign, so I hit the sign button, of every single number that I've put into list 1. Just above the 1 button, do you see where it says L1? I'm going to type second L1. Now you need to notice that I'm doing this in the heading of list 2. I'm not doing it in the first position of list 2. I'm typing what I want into the heading of list 2. The difference is, if I put what I want into the first position of list 2, it's going to give me the answer for the first position's answer. If I do it in the heading, it's going to give me the whole stinking column. Bam. You just now have to copy them onto your graph paper, onto your table of values. Take a minute and do that. And as I look at these, I need to keep in mind that the radians are basically my x values, and the green numbers that I got from list 2 in my calculator are basically the equivalent decimal of the exact values, but also my y coordinates. Still good? Okay, now when I'm putting this on graph paper, how you label your graph paper is uber important. But since there are 12 positions on a clock that I'm counting through, generally speaking, your graph paper is going to go out 12 boxes. Each box will be a pi over 6. Now, if you count that way, you're basically going to be treating these boxes like 1 pi over 6. Do you see how I do that? And if I think about the clock, every third box, 1, 2, 3, is an axis, or the end of a quadrant. 4, 5, 6, axis, end of quadrant. 7, 8, 9, end of quadrant. 10, 11, 12, end of quadrant. So thinking linearly through this graph paper, I've marked off basically the 4 axes. Can you see them? So when you're setting up your own graph paper, you want to have 12 boxes from the y-axis off to the right. You're going to go 3 boxes, call it pi over 2. 3 boxes, call it pi. 3 boxes, call it 3 pi over 2, that's 270. 3 boxes, call it 2 pi. Those are the only 4 I need you to label. You're welcome to label all of them. You must label those 4. Now, if you count that way, you can count any way you want, but this is the easiest one. Because then, essentially, I'm just paying attention to the red numbers from the list, from the column on the left. This is 0, and I'm going to go up 0. So I've made my first point. Now I'm going to go right 1, up 0.5. Right 1, up 0.5. Right 2, up 0.9. And by going right to, I'm going right to pi over 6's. Because remember, every box was a pi over 6. Do you see how nicely that works? So every box is now 1 pi over 6. And every time I have to go right 1, I basically just go right 1. 3 will be at 1, then it's going to start to come back down. Now I'm just going to fill these in. I hope you can follow what I'm doing here, because all I'm doing is plotting points. The next thing you need to know about a trig graph is it's a curve. There will never be points on these graphs, which is to say you will never end up with a graph that looks like this, and if you do, I will mark it wrong. These are nice fluid curves. There should not be any points on any trig graph, ever. In addition to that, there's always a high point and there's always a low point. And the high point always comes about 1/4 of the way through the graph, and the low point always comes about 3/4 of the way through the graph. The only exception to that rule is if I turn the graph upside down, which is to say I negate it. Still good? This is a sine graph. It's what a sine graph will always look like. We may flip it upside down. We may stretch it out like a fun house. We may make it taller, but it's always going to have this general shape, the sine graph. Other things I want you to know about this sine graph, and this is moderately important in terms of your ability to appreciate how everything ties together. I said pi over 2 was 90 degrees, or the end of the first quadrant. That means all this stuff in here was quadrant 1. All this stuff from pi over 2 to pi, that's 180 degrees, or the end of the second quadrant, is quadrant 2. Sine is positive in quadrant 1 and 2. What happens when I get over here in quadrant 3? It goes negative. Is it supposed to? Yes, it is. And here's quadrant 4. And that's how you linearly separate the quadrants on a graph. Can you see it? Okay, that is the sine graph. We're going to move on now to the cosine graph. Turn the page. Okay, now as you look at this, I've filled in my table of values. Again, I was just counting from 0 up to 12 by pi over 6's. So when you do this at home, you're going to have to write your own pi over 6's. But just remember, you're counting 0, pi over 6, 1, pi over 6, 2, pi over 6. I've done that for you for ease of use. The values I got in the y values, gosh, they look really familiar. And the reason that they look really familiar is, remember, the sine of A and the cosine of B, they're all the same thing. So I'm seeing these same numbers over and over and over again. I'm just seeing them now in a different order. I got these straight from my calculator by doing exactly what I promised I would do. I left list 1 the same. The radians have not changed. I just cleared out list 2, and in the heading for list 2, up where the L2 is, I typed in cos of list 1. And list 2, cos of list 1 is again using the second 1 buttons. Once I got those values, I transferred them to my table, and now I'm going to plot points. This effectively says that you should go right 0 up 1, or put a point right here. Then I'm going to go right 1 up 0.9, or put a point right here. Then I'm going to go right 2 up 0.5, put a point right here. Right 3 up 0, put a point right here. Do you see how easy this is? Let's keep going. After that, my values go negative. Now the significance of that is what? That's quadrants 2 and 3. And what does cosine do in quadrants 2 and 3? It goes negative. And last but not least, 0.5, 0.9, and 1 again. There's my quadrant 4, and it is back in the positive direction. Now the last significant thing I want to point out to you about this graph is that sine and cosine are so interrelated that if I were to take this graph, and you can't do this, but you can watch me do it, and shift it to the right 90 degrees, it becomes the sine graph. They are the exact